Let's now consider how much work it would take for, let's say, a 70-kilogram astronaut to climb from here to here. That's a pretty bad labeling job. That should be a distance indicated by the arrows. But we have a 70-kilogram mass going from here to here, and look at this as if that's what it means. Again, not thinking too clearly when I drew it like this. The radius of the Earth will designate by r sub e, and the distance to which we're going to go by 2r sub e. This thing here represents a hypothetical tower, maybe with a kind of a spiral staircase going up so that we can walk from here to here. So let's just find out how long it would take, or how much energy it would take, for a 70-kilogram individual to climb from 1 Earth radius to 2 Earth radii, assuming reasonable work output per day. Or let's just at least see how much work it takes to get from here to here. Okay, at the radius of the Earth, the acceleration of gravity is 9.8 meters per second squared, as we know. If we go out to double the Earth radius, we can think of gravity as being spread out over a sphere and emanating from a point that's identical to the center of the Earth. At the radius of the Earth, it's spread out over a sphere that's equal in area to the Earth's surface. If we go out to twice the radius of the Earth, since the area of a sphere is proportional to the square of the radius, if we go to twice the radius, we'll go to 2 squared, or 4 times the area. So the gravity is going to be spread out over 4 times the area. If it's spread out over 4 times the area, it will have 1/4 the effect, and 1/4 the acceleration will result. We'll see some details about why you can, at least a plausibility argument for that sort of thing later. This is kind of a preview. But gravity then will be 1/2 squared, or 1/4 of 9.8 meters per second squared. So the acceleration of gravity will be roughly 2.5. This is 2.45, but we'll be slopping rounded off to 2.5 meters per second squared at this point. So we see the following situation. We have this tower, and we're going to climb up to a distance that's equal to 2 Earth radii. At the surface of the Earth, the base of the tower, we have the mass under the 9.8 meter per second squared acceleration of gravity. We'll have a weight of mg, or 680 newtons, as you can figure out. 70 kilograms times 9.8 meters per second squared actually comes out, I think, 684 newtons, just rounding to the nearest 10, 680 newtons. And the force at twice the Earth's radius will be mg at that radius, but remember, g at twice the Earth's radius is only about 2.5 meters per second squared, actually 2.45 meters per second squared, so that the weight, when we multiply mg, is only going to be about 170 newtons, actually about 1/4 of what it was, or exactly 1/4 of what it was when we were twice as close to the center. So we have this situation depicted here. The force versus distance experienced by the climbing individual decreases from 680 newtons to 170 newtons as we go from the radius of the Earth to double the radius of the Earth. Now the actual curve is like this, and you can think about why that would be true, because it's because of the inverse square proportionality here. So this is really something over r squared, and 1/r squared has a graph that's got this kind of shape. If we do a trapezoidal approximation, just averaging the 680 and 170 newtons, we can get an estimate of the work. Now we got to know what RE and 2RE are. We have to know the values of RE and 2RE, is a better way of saying that. RE, the radius of the Earth, is about 6.4 times 10 to the 6th meters. That's inside the front cover of your textbook. Using those values, we see that the work contribution between RE and 2RE is the average force times the delta R. The average force we're going to approximate by the average of these two forces, realizing that really the average force is significantly less than that. But if we average these two forces, we get 425 newtons. And we multiply that by the Earth radius, the 6.4 times 10 to the 6th meters, and you can substitute that in and multiply it out. We get 2.7 gigajoules, or 2.7 times 10 to the 9th joules.